All right, so today we begin our discussion of the notion of convergence of a sequence. That is the precise notion of what we mean by the limit of a sequence, which is something you have probably encountered before in calculus. And so I'm presuming that you know calculus. I know you've all taken calculus courses, and that you understand, why you should care about calculus. So the motivation for all this is, of course, calculus, but really you already know why calculus is an important thing. So the real motivation is to really make sense of calculus. Okay, so given that we all accept that calculus is an important thing, we want to really make sure we know what we're talking about when we're talking about calculus in a mathematically rigorous sense. Because I mean, for most people, when they take calculus, things are kind of swept under the rug in elegant ways. The professors kind of do a little stage magic with their hands, a little distractions, so you don't notice some of the logical gaps that are happening. Try to make things flow and make sense, but there are some logical gaps that need to be filled in the calculus, mostly in the definition of limit, which undergirds the entire idea of the derivative and the integral, as you know. So that's sort of our main thing, is really to make sense of the notion of a limit in its various guises. And this is, in a way, kind of parallel to the development of calculus, because Leibniz and Newton, they had strong intuitions about infinity and about limits that led to the calculus, but the foundations, the way that they were really thinking about these things, was a bit shaky. They didn't really, in a sense, know what they were talking about. They just had strong ideas about how things worked, and they were largely correct. It's just that the underpinnings for what they were doing were not really very solid. And it just was, this was noticed at the time. It just nobody really knew how to make sense of it. Famously, a guy named Bishop Berkeley wrote a critique of the calculus, a very scathing critique of the calculus. But such attacks didn't really bother mathematicians. Things seemed to be working. It could solve all these problems in mechanics and physics and stuff using calculus, and calculate areas of geometric figures that had been mysterious for a long time. So things were all, things seemed to be going fairly well, despite the foundations being a bit shaky. But the further that mathematicians went with calculus and looking at it, at the various facets of it, and trying to push it forward, after a little over a century, I guess, from the founding of the calculus, the foundations ended up having to be seriously scrutinized by mathematicians themselves. So there's kind of an internal development in mathematics that, the more calculus was used, the more depth that the subject was gone into, the more we really needed to know really what we were talking about, so that things made sense. Basically, there was a kind of crisis that happened where mathematicians themselves realized that they had brought themselves to a point where they couldn't go any further because nobody really knew what anybody was talking about. So to circumvent this crisis, to resolve this crisis, the foundations had to be shored up for the calculus. And so out of this, the subject of analysis was born. Essentially, Cauchy was kind of the one who really gave the first rigorous definitions of many things like limit and continuity. And so analysis really is just being careful about calculus. So analysis is just careful calculus. Okay, so calculus, but with the foundations in place. All right, so what we're going to do is look at the notion of a limit in the simplest scenario in which you encounter it in calculus, which is in the concept of a sequence. Okay, so sequences, come up naturally all over the place, and we want to understand the notion of a limit of such a thing. So first of all, let's just be clear on what a sequence is. A sequence is an infinite list like this, A1, A2, A3, so on, right, going out forever, where the AI are elements of the real numbers. Okay, and that seems a little bit informal, just saying infinite list. What do I mean by that in a more rigorous fashion? Well, what we have here is to each of the natural numbers we have assigned a real number, right? So really, this is just a function from the natural numbers to the real numbers. So more formally, we can say more formally, a sequence is a function from the natural numbers to the reals. Okay, so you just think about the sequence as this infinite list, but if you want to be really formal about it, it's the same thing as a function from the natural numbers to the reals. And more generally, you can have a sequence which starts basically with different labels, different sequential labels. So you can start from any integer and go successively, and that would be a sequence, right? And you see, you could formulate this as a function as well. So you'd have the subset of the integers, which is n naught plus 1, n naught plus 2, etc. This sequence here would just be a function from that subset of z to the real numbers. Okay, so sometimes sequences might start with, a0, a1, a2, right? So I just have to allow for that. But this is a basic idea, just an infinite list. Okay, and so just some quick conventions. You can specify a sequence by some obvious pattern, right, of formula that tells you what the nth term is in terms of n, or perhaps a recursion, a way to generate the sequence. Right, so this is the Fibonacci sequence. Starts 1 and 1, and then you just add those two to get the next one, and add the previous two to get the next one, previous two to get the next one, keep going like that. Okay, always to specify a sequence, and usually sequences are denoted like this, at least in this text. So you have an with the round brackets. Okay, so now we're getting right down to it. The heart of the matter is the concept of convergence of a sequence. So the simplest possible example that we can discuss probably is the sequence 1 over n. An is equal to 1 over n. So the sequence is 1, 1/2, 1/3, 1/4, 1/5, etc. Okay, pictured here. So you have 1, 1/2, 1/3, 1/4, 1/5, 1/6 coming in, right? And everyone knows that the limit of this sequence is, excuse me, I don't know what I was doing there. The limit of the sequence is 0, right? As n goes to infinity, 1 over n goes to 0. Okay, so any reasonable person who's ever, who's taking calculus, so everyone in the audience here, would agree that the limit of this sequence is 0. But we need to know what we really mean by this, okay, in a really precise sense. So probably your sense of what this means is something like this. Okay, so our conception of the limit of 1 over n being equal to 0 as n goes to infinity, what we basically mean is that 1 over n, right, the elements of the sequence, the terms of the sequence, gets really close to 0 as we go far out in the sequence. Okay, so the 0 here is to say that the terms in the sequence, they're getting close to this number, and then the n going to infinity, that means we're going far out in the sequence, right? So the further we go out in the sequence, the closer we get to 0. That's basically what we mean by this. The problem you have to imagine is that if we had a more complicated sequence, right, some much more complicated formula here, maybe it wasn't so obvious exactly the magnitude of these numbers, and we had some claim that the limit of that sequence was equal to some number or other, how we would actually verify that, how we would actually go about, being certain that a more complicated sequence really did have a particular number as a limit. So this all seems quite intuitive in this simple case, but when things become more complicated, we need to really know what we actually mean, because our intuition can fall short, and maybe you have different people making different competing claims about what a particular limit is, and so you need to be able to decide between them unambiguously with a rigorous definition to be applied that there can't be any exception to. Okay, so what you want to imagine here. So let's just focus on this particular claim here, this particular sequence and claim about the limit. So you say that 1 over n gets really close to 0 as we go far out in the sequence. And I'm going to play the role of the skeptic. Okay, so it's helpful to imagine this in an adversarial kind of way. So you're making this claim which everybody's agreeing on, but I'm being hard-headed and disagreeable just for the fun of it, and being skeptical and saying, well, I don't really believe you about this. You're using words like really close and far out. Right, these are qualitative words. I'm going to insist you be precise about this. I'm going to insist that you turn these qualitative words into quantitative words, so that there's no possibility for ambiguity in this statement. So our skeptic here is going to make a precise challenge. He's going to say, well, I'll be the skeptic. So I'm going to say, okay, you're saying that 1 over n gets really close to 0 as we go far out in the sequence. Well, I'm going to issue a precise challenge related to this. So you tell me that 1 over n gets really close to 0. So okay, so 1 over a million, right? 10 to the minus 6. You have to tell me. And you say that when we go really far out in the sequence, 1 over n is getting really close. So you need to tell me how far out in the sequence do I need to go before these 1 over n's are within, say, 1 over a million of 0. Okay, so here's my skeptic's challenge. I'm going to bet you that you can't tell me how far out in the sequence one needs to go in order to make the elements of the sequence within 1 over a million of 0. Okay, you're telling me that 1 over n is getting really close to 0, so that it should get within 1 over a million of 0. And you're saying that this happens, when we get far out into the sequence. So I bet you can't tell me precisely how far out in the sequence you need to go to make the sequence within 10 to the minus 6 of 0. Okay, so that's my challenge. And maybe you'd like to pause the video and see if you can figure out how far out in the sequence to go. So how big should n be before 1 over n is within 10 to the minus 6 of 0. So this isn't that bad. We just want to make 1 over n differ from 0, so 1 over n minus 0. And maybe in general, we would want to put some absolute values here. We're just measuring the distance from 1 over n to 0. I want to make that less than 10 to the minus 6. Well, this is just equal to 1 over n, right? So what I want is for, let me write it this way. So you have 1 over n is equal to that. So what we want is for 1 over n to be less than 10 to the minus 6, right? And so what we want is, well, 10 to the minus 6 is 1 over 10 to the 6. And so that is just the same as n being bigger than 10 to the 6. Okay, so as soon as n is bigger than 10 to the 6th, we'll know that 1 over n is less than 10 to the minus 6. Okay, so in this case, you can meet the skeptic's challenge as long as you take n bigger than a million. 1 over n is going to be less than 10 to the minus 6, then less than 1 over a million. Okay, seems pretty straightforward. So precisely then we can take n equal to, say, 1 million plus 1. right? Any n that's bigger than or equal to 10 to the 6 plus 1, a million plus 1, is going to work. Okay, so we can kind of visualize the situation like this. So here we have the limit of 0, the alleged limit point of 0, and we have this, we're going to say we're really zoomed in here, so this is 10 to the minus 6, right? And we have negative 10 to the minus 6. I guess it doesn't really, we're only really going to be focusing over here. And so what's happening is the members of our sequence, we have right here, right on that point at 10 to the minus 6, that is a sub 10 to the 6th, right? Is so a sub 10 to the 6th is 1 over 10 to the 6th by definition. And then the very next one, right, is going to end up in here. So this would be a sub 10 to the 6th plus 1, and then subsequent, entries of the sequence are going to be doing something like that. Okay, and so maybe looking at this, thinking about this picture, I, as the skeptic, I say, I see. So your sequence is here, and then here, and then here. It's marching along. But let me do something like this. So you've got me there. But what I'm going to do is, if I change my challenge, right? So now I'm going to say, so here's 10 to the minus 12, say. Okay, so I'm going to change my challenge. Now you failed, right? Your choice of the n equals 10 to the 6 plus 1, a million plus 1, that's no longer working because these few terms here, right, are clearly not, they're not small enough to end up in this interval within 10 to the minus 12 of 0. And well, you, as the believer in this concept of the limit being 0, should say, well, no, not so fast, right? I mean, you have to tell me, so I, the skeptic, have to tell you the interval here, how close to make it to 0, and then after the fact, you're going to tell me how big to make n so that it falls in here, right? So, of course, for most little intervals you draw around 0, that's going to exclude most of the elements of the sequence. So it's not fair to expect that you should be able to fit all of the elements of the sequence into some given interval. So the interval has to be given ahead of time by the skeptic, and then you're going to say, okay, how far along do you have to go before we wind up in that interval, within that distance of 0? Okay, so the skeptic is the one who's insisted on the hard numbers, right? So they give you a hard number of, in this case, in our original case, 10 to the minus 6, here 10 to the minus 12, and you have to meet them with a hard number, but they have to give you the hard number first that you're going to meet, right? They give you a hard number, and then you respond with one. They're not allowed to go back and change it, right? They make the challenge, they issue the challenge, the hard number, you respond with a hard number. Okay, not allowed to go back and change after the fact. So they can issue a new challenge, right? So now this now is a new distinct challenge from the original one. Right, so the original one was 10 to the minus 6. We answered, or you answered, excuse me. I was the skeptic. You answered with a hard number, and now maybe I issue a new challenge, right, with 10 to the minus 12, and all you would have to do is respond with a hard number. So, and it's no more difficult than it was last time, right? Because we want 1 over n, the distance between 1 over n and 0 to be less than 10 to the minus 12. And this is just the same as 1 over n. And just as before, this is the same as 1 over 10 to the 12. So 1 over n is less than 1 over 10 to the 12 is exactly equivalent to saying that, that 10 to the 12 is less than n. right? So again, as long as n is bigger than 1 trillion here, 1 over n will be less than 1 over a trillion. Okay, so that means we can take, so as long as our n is bigger than or equal to 10 to the 12 plus 1, we'll be in good shape. Okay, and you can see how this would go in the general case. So at this point, after 2 challenges, you being the astute observer that you are, you would say, well, this is going to follow a familiar pattern, right? Whatever error term, right? So whatever error the skeptic would allow, so if the skeptic gives some error, says, okay, I bet you can't make the distance between the terms in the sequence and 0 within this epsilon error, you'll be able to respond in kind, right? Because what you would want is for 1 over n minus 0, you would want that to be less than whatever the challenge issued by the skeptic is, and that would be me, and then you can respond to that challenge, because all you have to do to make 1 over n less than epsilon is make n bigger than 1 over epsilon. Okay, so epsilon here, doesn't have to be a particularly nice number, but 1 over epsilon just going to be some real number. You just take the, as long as your n's are bigger than whatever that real number is. So, you can take the integer, the next integer after, next natural number after 1 over epsilon, and start your n's there, and that will respond adequately to the challenge that I, the skeptic, have posed you. Okay, so this is the kind of way to think about what precisely we mean by the statement that the limit of this sequence is equal to 0. So what it means is that any skeptic coming along offering some positive epsilon, so this epsilon here would be some positive number. So your skeptic issues some positive number. You have to be able to respond in kind with a number that tells you how far out in the sequence you need to go to make that sequence within. Well, okay, so let's just stick with the particular case. So in this case, you'd have to say what n makes 1 over n within that epsilon of 0. Okay, so what this statement again means is, issued any epsilon greater than 0 from your skeptic, you have to be able to say how far out in this sequence. You need to be able to specify a natural number, after which your 1 over n's are within the skeptic's epsilon of 0. Okay, so you have to be able to satisfy any challenge issued by the skeptic, and then show how far out in the sequence to go to make the 1 over n's less than that epsilon of within 0. Okay, so this brings us arguably to the most important definition of this course, and that is the notion of a sequence being convergent. So a sequence AN converges, or AN is a convergent sequence, if there is a real number, okay, so this is going to be the limit real number, such that for any epsilon greater than 0, so this is your skeptic, okay, so your skeptic is issuing an epsilon greater than 0 and saying, I bet you can't tell me how far out in the sequence to go to make the sequence close, within epsilon of this A, okay, so the sequence converges if you can meet the skeptic's challenge. So the skeptic is issuing their epsilon greater than 0. So for any epsilon greater than 0 issued by your skeptic, you have to be able to produce an n. Okay, so there must exist an n. So this is the point in the sequence at which you need to go, right? Such that past that point in the sequence, we have that the elements of the sequence and this limit a, right, the difference between them is less than the challenge issued by the skeptic. Okay, so it's just what we talked about above, but written out in general. All right, so our sequence converges if there's an a in the real numbers such that for any epsilon greater than 0, there exists an n in the natural numbers, so that when little n is greater than or equal to big N, the ANs are within epsilon of A. Okay, so in other words, given this epsilon greater than 0, you have to be able to identify the tail of the sequence, right? At which point, is it the case that after that in the sequence, all of the stuff after that is within epsilon of this A. All right, so try to say that in a number of different ways, give you ways to hopefully absorb it. And we say in this case that our sequence AN converges to A, and we write, just like in calculus, limit as n goes to infinity of AN equals A, or just the sequence AN arrow A, right? This AN sequence is going to A, approaching A. All right, so you should take some time to live with this definition, and hopefully it'll start making sense. I definitely remember when I was taking analysis, before I understood analysis fully. I remember spending a lot of time with this definition just in my head, just kind of going over it, thinking about it from different vantages. I found the way of thinking about it in terms of an adversary or an opponent or a skeptic to be really helpful to be able to write down this definition. So you should practice carrying it around in your head, when you're brushing your teeth in the morning. Try to see if you can remember what this definition is, formulate this definition. You should try to write it down and compare it to the definition you see here or in the book until you have it mastered. All right, so this is definitely very important. You definitely want to work on this if it doesn't seem totally clear at the moment. And of course, we'll be working with it throughout this lecture. So there's ample opportunity to get used to it before the end of the lecture. Okay, so let's just try to visualize this to get an idea of what's going on. So we have our sequence, right? A1, A2, A3, A4, a claimed limit A, and here is the epsilon here. So you want the distance between these ANs and A to be less than epsilon. Right, so all of the stuff that is within epsilon of A, you go epsilon to the right of A and epsilon to the left of A, right? And so what you're looking for is you're looking to find a point in the sequence after which everything in the sequence falls into this interval. Okay, so we have A1, A2, they're outside this interval. A3 happens to fall inside that interval, but that's not the point after which the sequence is going to remain in that interval, because A4 is over here. Okay, and then we have A5, A6, and then maybe at A7 we fall in the interval, and then after that it's going to remain in the interval. In this case, I'm just making up an example here. Okay, and then sort of stays close to A after that. Okay, so this would be, at least for this particular epsilon, we're able to meet the challenge here. Maybe if we zoomed in even more, looked at a really small interval, maybe things would stay in this bigger epsilon region around A, but they wouldn't, maybe it wouldn't work for some smaller epsilon. Okay, so you have to be able to do this for any given epsilon. And if you're issued a new epsilon, you have to be able to, say how much further out in the sequence you have to go to meet that one. Okay, but this is the picture of the situation, and this interval around A here, it's useful to have some notation for that interval. So this thing is, the book has I think kind of odd notation for it. The book calls it V sub epsilon of A. And it's really just this interval that extends to the right by epsilon and the left by epsilon of around A. But by far, I think the more common notation is B, B being for ball. So the ball of radius epsilon around A here, this is just all of the points, so this is all of the y in R that are within epsilon of A. So the distance between y and A is less than epsilon. Okay, so this is the open ball. So this is the open ball of radius epsilon about A. Or even shorter, you can just say the epsilon ball around A. Or the book's terminology, they say this is the epsilon neighborhood of A. Okay, and so the B is more common. B for ball. If you think about this in 3 dimensions, right? You fix some point. You look at all the points that are within some specified distance of that point. That's just the inside of a sphere in 3 dimensions. So you would get a ball, right? Okay, so it's not so interesting for the real line. You just have this open interval that extends to the right and left. So not so exotic here, but it is useful to just have this notation because it's actually easier to write this than to write the interval. Right? They actually write the A minus epsilon, A plus epsilon. It's a lot more symbols to do that than to do that. Okay, so we have this epsilon notion of an epsilon ball around a point, and so we can reformulate this definition of convergence in terms of the epsilon ball, because all this is saying is that given any epsilon ball around A, right, given any interval like this around A, you have to be able to find a point in the sequence such that after that, the ANs are within epsilon of A. Well, that just means that the ANs are in this epsilon ball, right? The ANs are falling in this interval. Okay, so convergence just means that given any epsilon ball, you can go far enough out into the sequence so that the members of the sequence are falling inside that epsilon ball. Okay, so I'll write down that geometric reformulation. Okay, so geometric reformulation, a sequence converges. That means that there's an A and R, such that for every epsilon greater than 0, you can identify a natural number so that for every element of the sequence after that natural number, that element of the sequence falls into the epsilon ball around A. Okay, so you put a little ball around A. You have to be able to identify some point in the sequence after which everything in the sequence is falling in that epsilon ball. That is the definition of convergence, just stated a little bit more geometrically, just formulating this inequality condition as this sort of nice intuitive idea of this ball around A, right? Sort of this, like A sort of puts this boundary around itself, and if you can always get the sequence inside that boundary after a particular point, then that means your sequence is converging to A. All right, so let's get a workout with the definition by looking at an example. Because we did 1 over n in a way. We didn't write it up nicely, but we talked about 1 over n. So we'll talk about a related example and do 1 over the square root of n. Okay, so basically here, what we're going to do is write a proof that 1 over square root of n converges to 0. Okay, and so what do we have to do to prove such a thing? Well, we have to show that that with this sequence and with this A, that we satisfy the definition, right? So what we have to do, so let's take a look at it. We have to say, so our A here is 0, our AN is 1 over square root of n. And so what we have to say is that, for any epsilon greater than 0, which is given, we have to produce a capital N, and then show that when n is bigger than or equal to that capital N, it's the case that the members of the sequence are within that epsilon of A. Okay, so this is just our skeptic's challenge. Okay, so what we have to do, we're going to start with writing our proof with let epsilon greater than 0 be given, right? That's our skeptic issuing their challenge. They're saying, here's your epsilon, good luck beating it, right? That's the And that's exactly the structure of this definition. So first, an epsilon greater than 0 is given. And for any such epsilon greater than 0, we have to produce an n. So we're going to let epsilon greater than 0 be given. This is essentially the first line of any convergence proof. Okay, that's your skeptic has issued their challenge. Now, according to the definition, once that epsilon is greater than 0 is given, you're supposed to produce a natural number n. And the big question is, where does this natural number n come from, right? It might seem like you're supposed to somehow pluck it out of the air. It's supposed to fall out of the sky into your lap somehow. And I don't recommend waiting for that to happen. You want to go looking for it. So this is where the real work is. You have to figure out what this n should be for a given epsilon with your particular sequence. Okay, and the key is what you want ultimately at the end. You have to show that, right? So you're trying to pick this n in such a way that when the little n's are bigger than or equal to that n, right, then an minus a is less than epsilon. So this is the key thing here. You want to identify when is it the case that a little n is within epsilon of a. Okay, so this is your target here. This is the condition, the main condition that has to be satisfied at the end. Okay, so that is the thing that we use to figure out what our capital N is. Okay, so what we do here is I'm going to look at, so I have my an, I want my an minus a to be less than epsilon, right? That's what I'm going to want, and I need to figure out, what range of n's should this be? Where should I start the n's from in order to make this the case? Okay, well, in this case, I have my my sequence, and I have my a. So I have 1 over root n minus 0, and what I want is for that to be less than the epsilon that I've been issued. This is just straightforwardly 1 over the square root of n, right? So what I want is 1 over a square root of n to be less than epsilon. And I know that this is equivalent to, and so basically what you want to do is kind of, we're looking for the condition on n, right? How big should n be? How far out in the sequence should I be to make this work? So you're kind of trying to solve this inequality for n, so to speak, right? So what we can say is, let me write it this way. So this is equivalent to, this is just scratch work here, okay? So this is scratch. You always do scratch work first. So we have 1 over epsilon less than square root of n, and then that is going to be equivalent, right? So these quantities are positive, epsilon's positive, so we can just square both sides here. We have 1 over epsilon squared less than n. Okay, so we find that as long as we take, as long as our n's are bigger than 1 over epsilon squared, then this should all work out, right? So as soon as, so the n's that are going to work are all of the ones that are bigger than 1 over epsilon squared. So what we can do is take, we can take our capital N to be, right, so that's going to be the start, the capital N is just the starting point of the little n. So where do you want the little n's to start? Well, anything that's bigger than 1 over epsilon squared is going to be fine. So you just can say, okay, let big N be any integer, any natural number which is bigger than 1 over epsilon squared. And we know for any given real number, right, we can find a natural number bigger than it. We discussed that when we discussed the real numbers. That's the Archimedean property of the real numbers. So letting epsilon greater than 0 be given, choose any n, any big N in the natural numbers such that n is bigger than 1 over epsilon squared. Okay, so that is as long as we take this n as our starting point for the little n's, right, all our little n's will be bigger than 1 over epsilon squared. We should be able to reverse all of this. Okay, so that is our big N. Okay, and this was all just scratch work down here, so I'm free to now, I'll erase that, I've figured out what my n should be, and then what do I have to do with it? Let's just go back to our definition. What I have to do is I have to show that past that point in the sequence, the members of the sequence are within epsilon of A. So what I need to do is show now that this inequality holds when little n is bigger than or equal to that big N. So if little n is bigger than or equal to big N, right? So if I'm at this point in the sequence or further, then what I need to show is just that the a n's are within epsilon of 0. Then, and we can just do a little computation. So then my a n, which is just 1 over square root of n, the difference between that and 0, and you're going to notice you're just repeating the computation you did before. All right, so this is 1 over square root of n, and what do we know about this? So what we're trying to say is that all of this is less than epsilon, right? I want to get a less than epsilon at the end here. So essentially I'm just going to be doing some inequality work. So let's see, n is related to big N, right? So we have n related to big N related to epsilon. So I want to get epsilon at the very end. So I'll follow little n to big N to epsilon. So little n here is bigger than or equal to the big N, and so that means that 1 over, right, so this is clear, so then 1 over n is less than or equal to 1 over big N, and so 1 over the square root of n is less than or equal to 1 over square root of big N, right? So this is less than or equal to 1 over the square root of big N. And you can assume that your reader is competent enough to be able to ascertain this from this, or this is just simple arithmetic, so you don't have to show your computations about that. That's basic. And then similarly, this big N, right? When we invert this, 1 over n is so our 1 over, so square root of n, right? So very similarly, so n bigger than 1 over epsilon squared. That means that the square root of n is bigger than 1 over epsilon, and that 1 over the square root of n is less than epsilon itself, right? So this is less than epsilon. Okay, so that finishes the proof then. Okay, that really is it. The proof is actually really short once you figure out what your big N is. You do some scratch work, you go through a bit of computation, but then once you have that, your first line is let epsilon greater than 0 be given. You say how your N is chosen, right? Which when you're reading the proof looks mysterious, right? Because when you're reading the proof, you're seeing this N before without seeing where it came from. And where it came from is examining this computation at the end. So in a weird way, these proofs are kind of written backwards. Logically, they're written backwards from the way you actually think up the proof. Okay, so the proof is nice and short and tidy because you're kind of hiding the messy stuff, the messy steps of how you figured out how to get big N. You're not under any obligation to show how you reason to get big N. You just have to show that whatever N you found works. Okay? That's all you're required to do. Okay, so let's look at another example and see if we can't make this make even more sense. So we're going to show that this sequence here, n squared over n squared minus 1, and this is, see here, n is bigger than or equal to 2. Okay, so in this case, right, n equals 1. This isn't well defined, so our sequence here is starting somewhere different than 1. But we're going to show that this sequence converges to 1. Okay, so our proof. So again, in the proof, get in the mindset, right? So what's happening here? You have this skeptic who doesn't believe that this thing is getting close to 1. So they're going to issue you an epsilon, right? So you let epsilon greater than 0 be given. So that's given to you by your skeptical opponent. And then what do you have to do? You have to show that this sequence is going to be within epsilon of 1 once you get far enough out into the sequence. Okay, so you're going to choose n in the natural numbers such that what? Right, so you have to see this is the n that's telling you how far out in the sequence to go. Well, we need to do a bit of computing first to figure out what that n should be. And again, you're guided by what your goal is, right? So what is your goal? Your goal is to figure out, your goal is to make the sequence n squared over n squared minus 1 within epsilon of 1, right? So the difference between your sequence elements and 1 is going to need to be less than epsilon at the end of the day, right? So that is what you're striving for. And we can do that by simplifying in here a bit. Okay, so just do whatever obvious algebra. And what we can do is make this 1 n squared minus 1 over n squared minus 1, and then a quick little, just some mental algebra will get you that. Okay, so this is your left-hand side, and of course that is just, you can remove the absolute values because 1 over n squared minus 1 is positive. And so what you would like is for, and again this is just scratch work so I don't have to make it look nice. So what you're looking for is 1 over n squared minus 1 to be less than epsilon. Okay, so this is the condition that's going to tell you how your n's should be chosen. So kind of solve this inequality for n then. So what we find is 1 over epsilon needs to be less than n squared minus 1, or that n squared needs to be bigger than 1 over epsilon plus 1, or finally that n needs to be bigger than the square root of 1 over epsilon plus 1. Okay, so that's how we're going to choose our capital N. So as long as your n's are bigger than this number, right? So this capital N is the first one of the little n's, right? So you can start at any natural number which is bigger than that quantity there. So choose capital N in the natural numbers such that n, big N, is bigger than the square root of 1 over epsilon plus 1. Right, and epsilon's positive, 1 is positive, so this is just a positive real number, and positive real numbers have square roots, as we found out, as we already knew, but found out really for sure last time in class. So now that I have written down the condition on my n, I can erase all the scratch work for how I got it. Okay, so you choose your n, so this is the point after which in the sequence you want to look. And what we have to show is that after that point in the sequence, it really is the case that the sequence is within epsilon of our alleged limit. So then what you're going to do is look past that point in the sequence. So if little n is bigger than or equal to that n, what you want to say is your sequence elements are very close to 1 in the sense of this epsilon, right? So you're within your skeptic's epsilon of 1. So if little n is bigger than or equal to big N, then what we have is that the distance between n squared and n squared minus 1 and 1, we already did this. Computation. This is just the absolute value of 1 over n squared minus 1, which is just 1 over n squared minus 1. And then your n squared minus 1, since little n is bigger than or equal to big N, right, this gets flipped around. So you have 1 over, you can replace the little n with big N. Okay, so little n is bigger than big N, so little n squared minus 1 is bigger than or equal to big N squared minus 1, and so the direction gets flipped when you invert that, and then your big N is bigger than this thing, right? So with it in the denominator, this is going to be less than 1 over, write this square root of 1 over epsilon plus 1 squared minus 1. And of course, squaring gets rid of the square root, the 1 and the minus 1 cancel, and you have 1 over epsilon, which is just equal to epsilon. And ultimately, we have our ANs minus 1, absolute value of that is less than epsilon, right? So we are finished our proof. Okay, so that is the whole proof there. Okay, so the book doesn't talk too much about divergence. It puts it off a bit, and I don't know. I need something to kind of fill the time here, and I think that it's good to look at divergence. I mean, you can kind of sharpen your intuition for convergence by looking at divergence carefully. So I'm going to use divergence to contrast with convergence, and it'll give you a workout with the logical quantifiers and just give you more to think about. So, of course, a sequence diverges if it doesn't converge. Okay, so that's simple enough. But what does that really mean? So it's helpful to look at the definition for convergence as a logical sentence. Okay, so what does it mean for a sequence to converge? It means that there exists some number in R, right? So there exists a real number. That's the thing that we're converging to, such that for all epsilon greater than 0 that your skeptic issues you, you have to be able to find a natural number, right? Okay, so there exists a natural number such that for all of the natural numbers after that one, so this is the everything past that point in the sequence, it's the case that such that for all n, let me say it this way, such that for all little n, whenever little n is bigger than or equal to big N, that implies that an minus a in absolute value is less than epsilon. Okay, so that's the structure of convergence. And so that's what it means to converge. Okay, so what does divergence mean then? Well, we just have to negate this, right? It's just the divergence, sequence diverges is just the logical negation of converge. So we change this existence quantifier into this universal quantifier, right? So that this means for all real numbers. All right, so we'll just do a straightforward changing the quantifiers with a negation, then we'll talk about why it makes sense intuitively, how to think about it. So then that there would exist an epsilon greater than 0, such that for all big N, there exists a little n, such that, and then we have to negate this implication here, right? And the only way this implication is false is basically if I'm telling a lie, right? So if I'm giving you this statement, this thing implies this one, or whenever this is true, this has to be true. The only way I'm lying to you is if this is true and this is false, right? So that would mean that n is bigger than or equal to n, and this other thing is false. So the negation of this thing holds. Okay, so this is divergence. So let me give the definition of divergence. Okay, so here it is. So just written out, just taking the same logical sentence and just writing it out with a bit more English in it. So a sequence diverges if for any real number there exists an epsilon such that for all natural numbers there is a natural number which is bigger than or equal to that natural number, and such that for that n, right? So we're just thinking about a particular n which is bigger than this big N, and such that the corresponding element of the sequence is a distance bigger than or equal to epsilon from A. Okay, so that's what it says just with more words. Okay, so colloquially then, what this definition is saying is that a sequence diverges if it doesn't converge to any particular real number. So that is, if the skeptic can win their challenge for any claimed limit. Okay, so a sequence diverges if whenever you, the person who's saying that the sequence is converging to some particular A, right? So you have some A in mind, you say my sequence is converging to this A, the sequence diverges if the skeptic can win their challenge for that claimed limit. Okay, so let's go through this. So sequence diverges if for any A, so this is the claimed limit, right? So you now are in the losing position. I'm in the winning position as the skeptic. So you have this A in mind as the limit. And I say, well, here's your challenge. So here's an epsilon greater than 0. Okay, so I'm the winning party here. So I'm producing an epsilon challenge for you, and you can't win that epsilon challenge. And what that means is that no matter what big N you try, right? So you're supposed to say that you're supposed to specify how far out in the sequence to go such that the sequence is within epsilon of A. But no matter what you try, right? So that for no matter what N you try, at some point after that N, your sequence is going to disappoint you. Okay? So I issue a challenge, and no matter what you try, you go a little bit further out in the sequence, and the sequence pops away from A by at least that epsilon that I've issued, right? So your sequence is not within epsilon of A at some point after any particular N, right? So no matter what N you choose, you can go out a little further and your sequence is going to let you down. Okay, so I win because I've produced an epsilon and you can't get your sequence within epsilon of that A no matter what big N you try. Okay, so that's all this. So this definition. So we started just on the logical quantifiers level to be careful. Wrote that down more in words, and hopefully you can see how those words line up with the skeptic game that we are playing for convergence. So divergence just means skeptic wins. Okay, convergence, you win, good guys win. Divergence, skeptic, me, bad guy gets to win. Okay, and so a typical divergent behavior, you probably are familiar with this, but sequence getting infinitely large, that would be typical divergent behavior. Also, aimless wandering, right? If your sequence is just kind of wandering around and not settling down, doing anything in particular, just kind of, all over the place, or bouncing back and forth between a few values. That's just sort of another, I guess, form of aimless wandering. So those would be typical divergent behavior. And so for example, so we can consider, so we'll show that A, N just equaling N diverges. Okay, so of course this getting infinitely large, just sort of getting bigger and bigger and bigger, not expecting that to settle down to anything. That would be the convergent behavior, so we should expect this to diverge. So our proof then would be, well, to start a divergence proof, the claim that this diverges means it doesn't converge to anything, right? So we start with the anything. So let A in R be given. So that's going to be your, this would be sort of the candidate for convergence, but we're going to show that it doesn't converge to that no matter what candidate you're given. Right? Given some arbitrary candidate for convergence, it doesn't converge. So given some arbitrary candidate for convergence, what we're going to do is we have to, so we're in the role of the skeptic, right? We're going to be, the skeptic is going to be the winner in the divergence. So the skeptic is going to choose an epsilon, is going to issue an epsilon challenge, which is a winning epsilon challenge for the skeptic. So let A in the real numbers be given, choose epsilon equal to, well, we need to figure out what this epsilon challenge, this winning epsilon challenge is going to be. And you can visualize the situation. So A, this is the claimed limit. And then the skeptic is going to say, well, if I put some epsilon neighborhood around this, some epsilon ball around this, no matter what, no matter how far out in the sequence you go, if you go a little bit further, it's always going to be outside this thing. And so, intuitively, this is always going to work. I mean, no matter what size this neighborhood around A is, eventually the ends coming along are going to get further out here. Right? So it really doesn't matter what epsilon is going to be, because the ends are just going to keep marching along and keep going along to the right, and they're going to end up outside of that epsilon ball. So we're going to just take epsilon to be equal to 1. Right? You could really take epsilon to be anything, but we'll choose, just for definiteness, epsilon equals 1. You only have to win one challenge as the skeptic to have divergence. And now we, as the skeptic, we have to show that our opponent is always going to fail. So no matter what big N they pick, no matter how far out they go in the sequence, we can always find some point further in the sequence that falls outside of this epsilon neighborhood here. So we're going to choose epsilon equal to 1 and let n, big N, in the natural numbers be given. Choose epsilon equal to 1 and let big N be in the natural numbers. Okay, so what we need to show is that at some point after this big N, wherever this whatever this big N is, the sequence is going to be outside of this this epsilon ball here. So to figure out what the little n, right? So what we have to do is produce a point past this point in the sequence. So we're the skeptic, and our opponent is desperately trying to say, okay, here's your big N, this one will work, and you have to show as the skeptic that it's going to fail, right? So at some point after this, we're going to have failure. So in other words, at some point after this big N, we're going to be outside of this thing, right? And so intuitively, this sequence just coming along here, right, it's going to be, the N is going to be bigger than A plus 1 at some point, right? So as long as this little n here is bigger than A plus 1, then we as the skeptic are going to win, right? So all we have to do is take our little n to be bigger than A plus 1, and, well, we also, by definition of this, of this game, we need our little n to be bigger than or equal to the big N, right? So we just need our little n to be bigger than this this A plus 1, and actually just bigger than or equal to A plus 1. Right, even if n was equal to A plus 1, that would still be not within 1 of A. We'd be just on the boundary there. So what we can do is consider little n such that little n is bigger than or equal to big N, and little n is bigger than or equal to A plus 1. Then all we have to do is look at the difference between AN and A, and AN is just n, right? So this is just n minus A. And n minus A, that's bigger than or equal to 1, right? So we know that n minus A has to be positive, and so the absolute value of n minus A is just n minus A, and that's bigger than or equal to 1, and 1 is equal to epsilon by definition. Right? That's what we had to do. We had to say that that our sequence ends up further away than epsilon from A. So this is our complete proof here. And so this proves the divergence. Okay, so we'll try another one, very different kind of behavior. This is a bouncing around one. So when n equals 1, this is just 1. When n equals 2, it's -1, and then it's back to 1, -1, right? So what we have is we have -1 here, and we have 1 here, and our sequence is just bouncing back and forth between these two poles here. Okay, so sort of course, that's, intuitively not going to diverge, or sorry, not going to converge. It's going to diverge because it's not going to settle down to anything, right? It's not going to stay near any particular real number. So I think we have that simple picture we can keep in our mind without too much trouble. So our proof here. So we need to show that it doesn't have any particular limit, right? There's nothing it's particularly converging to. So let A in the real numbers be given. Okay, so A in the real numbers be given. And what we have to do is choose an appropriate epsilon, because we, believing that this is going to diverge, we think ourselves the skeptic, and so we have to issue an appropriate epsilon challenge that cannot be met. And it's not really too hard to see that if you take any real number, an interval of length 2, so extending 1 on one side and 1 on the other side, is not going to have, it can't contain both of these points, -1 and 1 at the same time, right? I mean, intuitively, -1 and 1 are a distance of 2 apart from each other. So an open interval of length 2 is going to fit very neatly between -1 and 1 without hitting either one. If you take such an interval and you move it a little bit to the right, it'll contain 1, but not contain -1, right? So the sequence would jump out of that interval. And if you move such an interval to the left a little bit, it would contain -1, but not contain 1. And so the sequence would jump out of that interval when it hits 1. So any interval of length 2 is not going to contain at least one of these points. And so what we can do is take epsilon equal to 1 here. So let A in R be given, set epsilon equal to 1. And then we claim that that's going to work. So we'll then set epsilon equal to 1 and let big N be in the natural numbers, okay? Because this is we're the skeptic. Our opponent is desperately trying to produce this N, so they're going to give us a big N and claim this works, and then we have to show that big N actually doesn't work. At some point after that big N, the sequence ends up further away from this A than 1. All right, so we need to think about our situation here. So basically, we have our A here, and we have our little interval of A plus 1, A minus 1, right, on either side, extending our epsilon equals 1 on either side. Okay, so this is A plus 1 here. And clearly, so there's some clear situations in which so you might think, so basically, I mean, this A is arbitrary, and so things can, the situation might be different depending on what A is. So, if A is, if let's say if 1 is here and -1's over here, then clearly, it doesn't really matter what this N is. The sequence is jumping back and forth between these two, and it's just never going to fall in this interval if A is far enough over here, right? Or if A is, if the situation looks more like, so if the situation looks more like, -1 is here and 1 is over here, then we have something similar. So if A is far over here, that would be another situation in which it's, it doesn't matter what our little n is, because our A is going to be too far away from these things for 1 and -1 to ever fall in this interval whatsoever. And another situation would be if your A, if your A is equal to 0, so if you have A equal to 0, then you have your, then 1 is here, -1 is here, and your interval just cosily fits in between them, 1 and -1 don't actually fall in that interval. So again, it doesn't matter what little n you pick after this n, because your sequence is always avoiding being inside that interval. And so the skeptic would win. But there is a range in here. So if a moves to the right a little bit, then all of a sudden 1 is falling in this interval. And it's -1 that's going to end up outside of the interval. So that would be our winning n whenever we get -1. So that would be the case if you move a to the right for a little bit, and if you move a to the left for a little bit, then -1 falls in this interval. So you have to look for the little n where you get 1 here. Okay, so it seems like there's kind of a lot of cases here, but it actually turns out that you can handle this in just 2 cases. So you can do it for a being bigger than or equal to 0 and a less than 0. So if a is bigger than or equal to 0, so going over here, then it might be that 1 falls into this interval here if a is appropriately positioned, but -1 is never going to fall into that interval. Okay, so we can just look for the little n that's after big N here that hits -1, and then that's not going to fall in that interval. And then it would sort of be the opposite. If a is less than 0, then 1 never falls in that interval. Okay, so that's the basic idea, is to just determine, right, so either do a bunch of different cases if you don't see how to do it in just a few, or you figure out that really it only matters whether a is plus or minus. You can get away with just those 2 cases. So what we're going to do is we consider 2 cases. Consider 2 cases. Okay, so case 1. Case 1 is that a is bigger than or equal to 0. Okay, so then if a is bigger than or equal to 0, right, so we have all this stuff, and we're additionally assuming that a is bigger than or equal to 0. So it's either the case, so either, let me say it this way, sorry. So either a sub n, right, so remember we're starting at this point in the sequence, either a sub n equals -1 or a sub n plus 1 equals -1, right? Because the sequence is just bouncing back and forth. So we're looking for the one where it hits -1, right? Because we know that's going to be to the, our a is to the right, and this, when it hits -1, that's going to fall outside of the interval of this epsilon ball around a. So we set n equal to n or n plus 1 accordingly. Okay, then all we have to show is that an, the difference between that and a, is bigger than or equal to epsilon. Okay, so, well, then your an is -1. So -1 minus a, well, that is just equal to 1 plus a, right? Because a and 1 are both non-negative. So we know that that 1 plus a, that's the positive, that's the absolute value of -1 minus a. And a is bigger than or equal to 0, so this is bigger than or equal to 1, and 1 is our epsilon. So indeed, this an is a distance greater than or equal to epsilon from a, and so we, as the skeptics, win. And then the second case is a less than 0, and we basically just copy the proof, except now we're going to look at 1. So either an equals 1 or an plus 1 equals 1. And we set little n equal to big N or n plus 1 accordingly. And then in this case, we're looking at absolute value an minus a. That's equal to 1 minus a, absolute value. And minus a is positive, so 1 minus a itself is positive. and then minus a is less than 0. That means, a is less than 0, minus a is greater than 0, so this is greater than 1, and 1 is equal to our epsilon. So in either case, we find that we have an n, a little n bigger than or equal to our big N, such that an is greater than or equal to a distance of epsilon from a, and we as skeptics win. Okay, so our opponent wasn't able to produce the required big N. We were always able to beat them no matter what big N they produced. Okay, so that actually is basically the end of the meat of the lecture, the concept of convergence and working with convergence and the negation of convergence, which is divergence. And in the last few minutes, I just want to throw something in here. We'll use this at the beginning of the next lecture, so it's important. I don't want to waste time. So this is the technique of the triangle inequality. This is a very useful inequality that comes up when you're doing convergence and divergence proofs sometimes. So the basic idea here is we have a triangle. I'm going to try to make it not look like a right triangle. Okay, so here's A and B and C. Okay, so we're thinking about this in the plane, and you can think about these these sides as vectors, right? So the difference, so A and B are A, B, and C are points, and the difference between them gives you a vector. And in any triangle, right, when you want to go from A to C, it's quicker to go from A to C than it is to stop off at B in the middle, right? So the distance from A to C is quicker than going A to B and then B to C, right? So intuitively, one thing we have is that the distance from A to, so let's say A to B. I mean, this works for any side of the triangle, right? So going A to B directly is quicker than than stopping off at C and going there, right? And you can do this for any side. So going from A to C is quicker than stopping off at B. Going from A to B is quicker than stopping off at C, right? You can do this for any combination of the sides. So the length of the side AB, or the length of the vector that goes from A to B or from B to A, is less than or equal to the sum of the other two sides, right? So A minus C plus B minus C. Or maybe I'll say it as a C minus B. That'll be more convenient for me. Okay, so that's one thing. So this is called the triangle inequality. Okay, so this is the triangle inequality, and maybe I'll put that down in a second. And there's another intuitive inequality as well here. The other one that's intuitive is that A minus B, so that AB side, is bigger than or equal to the difference of the other two sides. So we have A minus C, that side, and C minus B, that other side. And that's because, so think about this difference, the AC side minus the CB side. If you imagine taking this side here and laying it along the AC side there, the difference is whatever remains, right? And so whatever remains there, that's sort of clearly less than or equal to this other side, right? Because this, the one, right, when you lay this one along here, those whatever remains together with the BC side is just making a straight segment AC, but this AB here has to be put in at an angle, which indicates that that AB is bigger than or equal to that difference. So we have that, and in fact we can put an absolute value here because you might not know which one of these two sides that you're subtracting here is the bigger one. So it's whichever order of subtraction gives the bigger one. So we have an absolute value there. And so what we can do is rewrite these. So this top one here, the A minus B, you might notice that if we call this vector here, so if we call this V and we call this W, that v plus w is the a minus b here, so v plus w, right? And so what we find is that that v plus w, or what we've argued for, is that the length of v plus w is less than or equal to the length of v plus the length of w, and the length of v plus w is bigger than or equal to the absolute value of the difference of the lengths. Okay, and these are called the triangle inequality and the reverse triangle inequality. Okay, and this is kind of a heuristic argument that I gave up here with using this triangle, but it's and that it requires a bit of work to figure this out in 2 dimensions to actually make a rigorous argument out of this. But fortunately, for the real numbers, it's kind of a trivial argument to make that these inequalities hold. So you just take any 2 real numbers, and then there's just some cases. You just look at the different signs. So if they're both non-negative, or both negative, or one's non-negative, the other one's non-negative. There's really only 3 cases to look at. Those 3 cases that I just stated there. So you look at those 3 cases for each of these 2 points here, and you check that it works. So we'll be using these inequalities. They're very useful to use. Okay, so that's everything, and I'll start with some general propositions about convergence that will use this triangle inequality in the next lecture.